Hello friends, this is JBrains again, and welcome back to Adding Fractions, Fundamentals in Test-Driven Development, Evolutionary Design, and High Discipline Programming. When we left off, we had implemented equals to make it easier for us to finish implementing add. And so we're going to get back there and we're going to try to finish off add here, and we will see how it goes. Switching back over to our test list, we can now actually scratch out here in the upper right hand corner equals and hash code because we have here reduce in equals to remind us of the last little bit that we need to do. And so since we have reduce in equals here, it would be nice to get to the point where we need to reduce an answer as soon as we can. But before we do that, it's probably a good idea for us to find the test on this list that forces us to do the simplest additional thing. Remember, we're always looking for a test for which we only need to add one idea at a time. The last test we made pass was this one here, 1/5 plus 2/5 equals 3/5, because we got to ignore the denominator. What test will allow us, will force us to take the denominator into account without having to worry about doing anything particularly difficult or worry about multiple things? And I think that is this test up here, 1/2 plus 1/3 equals 5/6, because this allows us to use the naive algorithm for adding fractions. So I think we should start there. So now let's flip back over to our IDE. Let's open up add fractions test. I know this test class is starting to get a bit long. This is turning into a little bit of a junk drawer of tests, and so we'll probably figure out what to do with that a little bit later. But for now, let's add a new test. And this is, let's see, for now this is different denominators. That's probably the most we know about this test. And this test, now we get to write the test that we've wanted to write all the way along, the kinds of tests that we've wanted, or the format of tests we've wanted to write all the way along. And that's just a really straightforward assert that the sum of these two fractions is this other fraction. So 1/2 plus 1/3 should be 5/6. Let's run the test. And watch it fail. Expected 5/6, but was 2/2. Why? Because our current implementation ignores the denominators, in fact takes the first denominator and assumes that that should be the denominator for both fractions, and then just adds the numerators. So this is a nice little reminder that we still don't have reduce working either, but really what's important is that we finally need to actually do something with the denominators. Now, the simplest way to add this behavior and keep everything else working is to add an if statement for the new case, else do the old thing. So we can simply add something that says that if this denominator is not the same as the other denominator, then we need to do the new thing, otherwise do the old thing. And just to make it a little bit nicer, I'll add the braces in both cases. So we need to return something in this case. Let's just return anything to make sure that the new test still fails, but the old tests still pass, and they do. I just wanted to do this as a tiny micro step to make sure I got that if-else thing right. I wanted to make sure that this condition, whether the denominators are different, that this is actually the condition that I cared about. And so I don't actually want to return this. Here's where I want to just put in the obvious implementation and see if I get it right. So if I remember the algorithm, it should be this numerator, times that denominator plus that numerator times this denominator. And that's the numerator of the new fraction. So if we flip back over to our test list, we want 1 times 3 plus 2 times 1. That's 3 plus 2, that's 5. And that's how we compute the numerator. Computing the denominator is simpler. That's just 2 times 3 equals 6. So now we flip over to our IDE, and our denominator will be this denominator times that denominator. Now that is by far the most we've ever typed without running the tests. And you can see now why I wanted the separate micro step of adding the if block, even though the body of the if block for the true case, the stuff that we just replaced, even though I put something here that I knew was absolutely not going to fail. If I had tried to type all this in one go and it failed, I would have no idea where the failure is. This way, the way that I did it with the smaller steps, at least, I know that if I make a mistake, the mistake is definitely 100% in here somewhere. Well, let's run the test and see what happens. And huzzah, I made it pass. I'm happy with that, so we'll go back over to the test list. We'll scratch out that test and check in our changes. So we can add fractions with different denominators as long as we don't have to reduce the result. And that, again, gives us a little bit better clue about the name of the test. Different denominators without reducing the result. Or actually just without reducing, perhaps, is better. So let's run that test. Whoops, let's run that test to make sure it passes. And, unsurprisingly, I'm going to do exactly the thing that I did last time. I'm going to amend the commit because that's probably the name that I wish I'd used before. And the fact that I did that in 2 steps is really not that interesting. Excellent. So which test next? Looking at all the other tests, it looks like they all need me to do some kind of reducing. So if I had a test that allowed me to use the naive implementation but forced me to reduce, that would be best. So that's a case where the denominators have no common factor, but I have to reduce the result. Do I have one of those? It doesn't look like I do. So now I have a choice. Well, in fact, I don't even really have a choice. I could try to come up with that test, or I could just notice that, for example, 1/3 plus 2/3 equals 1, or 3/4 plus 3/4 equals 3/2 actually fits the bill because it forces me to reduce. And the fact that the denominators have a common factor doesn't really actually matter here. Whether the common factor is there or not just determines whether the fact that there is a common factor, I should say, guarantees I'll need to reduce. So now's a good time to implement the part of equals that was missing, and that is reducing. For example, I'll write over here on the test list, one of the simple tests would be that 6/8 is the same as 3/4. Now this isn't really even necessarily a test for reducing so much as it is a test for the constructor. I think it makes sense for us to reduce in the constructor. Normally I don't like constructors to do anything except assign values to fields, but this is one of those cases where it really does make sense to reduce in the constructor, in part because that's the requirement. The requirement is for fractions always to be in lowest terms, and so I'll write on construction is the best time to do it. And second, because it is something that happens entirely in memory, doesn't touch any expensive external resource, doesn't touch a database or a network, we can get away with it. So in the constructor, this test actually should be that if I construct a fraction at 6/8, it should actually be equal to 3/4. And the fact that equals just checks the numerator, compares the numerator and denominator, ensures that we'll get the behavior we want. So in fact, this is a test for reduced fractions. Even though it's a test for the constructor, again, I'm not testing the constructor method, I'm testing the reducing behavior. And if later on I move reducing to an explicit step with a reduce method, then I don't have to change the name of the tests. The tests didn't change just because the structure changed. So let's create a new test over here. And that's called reduce fraction test. And the first test that I can think of, in fact, before we get from 6/8 to 3/4, the first thing I can think of is that something like 3/2 stays at 3/2. So a fraction that doesn't need reducing stays the way it is. So let's try writing that test. Already in lowest terms. So we're not testing equals so much as we're using equals to test the behavior of the constructor. So this is going to look strange because it's going to look exactly like a test we already had for equals. Let's just go with it. Run the test and watch it pass. We hadn't needed to do anything. So this test is really there only for the sake of completion. Yes, it duplicates a test we already had, but it does so for reasons of clarity. If I were really concerned, then I could do something as simple as replace this body with a comment that says, we've already tested this in fraction equals test. And I would actually leave it as an empty passing test because it does pass. And I don't want to duplicate it somewhere else. But the duplication I think is okay this time. Now let's try reduce to anything but 1. So over on my test list, I'm going to add the fact that 3 over 3, for example, should reduce to 1. And I suppose we could say that 0 over 4 needs to reduce to 0. I'm not sure whether I care about representing that as 0 over 1 or something else. I'll think about that. But since I had the idea in my head, I just want to make sure that I write it down. It sounds like we've got a little rain brewing outside, or at least some heavy wind. I hope that doesn't come through too much. At any rate, which test? Let's try the 3/2 to 3/2 test. So it's actually not... Is it reduced to anything but 1? Now that I think of it, there's one more test, and maybe I just need to get more of the stuff out of my head. We also want to make sure, for example, that 8 over 4 reduces to 2. We probably want to make sure that negative 20 over 5 reduces to negative 4. I don't think that negative numbers will necessarily be a problem, but we should also probably make sure that 20 over negative 5 also reduces to negative 4, and maybe that negative 9 over negative 3 reduces to 3. I'm not sure that all of that will be needed, but we'll try it out and see what happens. So I think this reduced to anything but 1 is probably the wrong method name. I think I tried to get a little too clever a little too quickly. So with 3/2 already reduces to 3/2, so let's make sure that 6/8 reduces to 3/4. So let's see. Reduce to not whole number is probably closer to what we meant. So assert equals. The expected result is 3/4, and the fraction is 6/8. Let's see if that passes. It shouldn't, since we haven't done any reducing yet. Excellent. So now's the time when we can implement the algorithm that we need to make this work. Now, the algorithm that we need is called finding the greatest common divisor. So over here on my test list, I'm going to add GCD up on my to-do list. So what's this magic algorithm that I need to compute GCD? It's called Euclid's algorithm. It's the way I learned to compute the greatest common divisor when I was in school. And so I found it over here, of course, on Wikipedia. Now, this version down here is the one that I'm familiar with, but this one up here is the one I think we'll try. You can see the algorithm is pretty straightforward. You just put in the two numbers. In our case, it'll be the two denominators. And then there'll be this little bit of arithmetic that we'll do in order to compute the greatest common divisor. Now, whenever I'm typing in an algorithm that I am taking from somewhere else, again, I'm not doing test-driven development here. I am going to add some tests to see that I've typed the algorithm in correctly and that it does what I think it's supposed to do. So let's pop over here into our IDE, and let's start with, unsurprisingly, a test, greatest common divisor test. And I'm actually going to implement the algorithm right in here to start with and then figure out how I'm going to use it. So first, let's write our first test. The simplest test for, these are all going to be examples. And so the first simplest example that I can think of is that the greatest common divisor of 1 and 1 should be 1. So assert equals 1, GCD of 1 and 1. Now normally I don't like abbreviations like this, but this is such a standard mathematical abbreviation that I'm willing to put up with it for now. And as I said, I'm going to implement it just in here for now and then move it out to where I'm going to need it when I'm going to need it. So let's run all the tests to make sure that this fails. And it looks like our reduced fraction test also fails. It would be a good idea to back this out. So waiting to implement greatest common divisor. All right, and so we have just the one failing test so far. So of course, we'll remember where we need to go. Let's fake it till we make it. Let's go back to greatest common divisor tests. All right, and now we can just type in the algorithm and see if we get it correct. So while b is not 0, all right, so while b is not 0, okay, int t equals b, b equals a mod t, a equals t, and return a. Let's see whether by chance that already works. Whoops, run the tests. It passes, that's a good sign. So let's commit this. I probably should have committed before I actually typed the algorithm in. We'll see if that's a problem. Copied GCD algorithm from Wikipedia. So now let's add a whole bunch of tests and see if we got it right. And now I'm looking at these tests here. I'm going to do something that I don't ordinarily like to do. Instead of having a whole bunch of tests here in each in its own separate method, I'm just going to have one test here called examples. And we'll just keep adding examples, making sure they pass. So 2 should be the greatest common divisor of 2 and 2. That passes. Let's try a negative number. The algorithm is supposed to work for negative numbers. I'm going to make a note over on my test list that 0 should lead to an error. And we'll see what happens when we get to 0 in just a little bit. Now let's try greatest common divisor. The greatest common divisor, actually now this is a good time for a separate test method. So these examples are all reflexive, a number with itself. Now let's try a test for relatively prime. And these are all examples where the two numbers have no common factors. And when there's no common factor, the GCD should always be 1. So for example, the GCD of 2 and 3 should be 1. The GCD of 4 and 7 should be, 4 and 7 should be 1. Now I'm curious to see what the GCD of 2 negative numbers would be. I'm going to try 1, but it might be negative 1. Let's see what we get. We did get negative 1. There we are. So it's probably a good idea for us not, since our denominators are always going to be positive, it's probably a good idea for us, we don't really need to worry about the GCD of negative numbers, but just for the sake of completion. Now, what if one is a multiple of the other? So multiple, 1 is multiple of the other. Just because this is a little bit easier than jumping all the way to the common factor case. So for example, the GCD of 3 and 9 will be 3. And the GCD of, say, 5 and 25 will be 5. Let's make it 5 and 30, just so they don't look like squares. So far, so good. And now how about common factor? So for example, 2 is the GCD of 6 and 8. Yep. And just to choose another one, let's make it 7. So 7 is the GCD of 49, and I don't know, some big number, 315. Good. And just again for the sake of it, I assume -4 will be the GCD of -24 and -36. In fact, that leads me to ask another question. What's the GCD of... Oh, actually it's -12. Haha. Let's make it -24 and -32 then. By accident, I just chose numbers that happen. Now that becomes 8. Haha. About 24 and 28. Surely this time the GCD will only be 4. There we go. Now, what about the GCD of -24 and +28? Will that be +4 or -4? Let's see. It's actually +4. And then just out of interest, what about 24 and -28? That's -4. So that's interesting. That's actually interesting enough to move into their own test. And I'm going to put a comment here. Not sure whether I like this behavior. I probably prefer that GCD always be positive. So let's just take a quick look at the algorithm over here. Yeah, you know what? It might make more sense for our purposes to make the GCD always positive. So let me first check this in. Explore GCD algorithm from Wikipedia. Found an annoying aspect of its contract. So I'm going to change all these cases where the GCD is negative, where the expected result is negative. I'm going to make them all positive, and they'll fail. It should be 4 failures. And now I'm going to do something really simple here. And now they should all pass, and they do. All right, so now I'm pretty comfortable that GCD works. So I'll scratch that off the list. And I can use this to implement reduce. And that's exactly where we'll pick this up in the next and final I Promise You episode. Thanks very much for listening. I hope you enjoyed it, and see you next time.